Okay, let's start. Hey everyone, this is Charlie. I'm the co-founder and the principal of XCamp. Today we have the 2023-2024 season zero level live solution for this December contest. We are happy to have Max here. He's the ICPC, it's the college contest of the computing algorithms world finalist. Also, you may know XCamp. We are located in Silicon Valley. We provide coding classes for the students, especially on the competitive coding. Okay, great. So we are happy to have Max here. Max, how about you have an introduction about yourself?
Yep. Thank you, Charlie. So yeah, I'm Max, one of the instructors for XCamp. And yeah, also my credentials have already been stated by Charlie. But yeah, I'll be presenting today's solutions.
Okay, thank you. I will stop my screen sharing and turn the stage to Max.
Yep. So let's just go ahead and jump straight into talking about the problems. I'll just go ahead and do the explanations here on the whiteboard. So starting with the first problem. So the first problem was about towers and cows with weights. Yeah. So let's see. So we are given n we're given n distinct weights. So n is up to 2 times 10 to the 5, where we basically have we're given like things like pairs wi and ai both less than or equal to 10 to the 9, which means we have this means we have ai cows with weights wi. That's what this means. And so now we want to place them all into towers. So we have a total of m less than or equal to 10 to the 9 towers. And what we want to do is and we have some parameter k also less than 10 to the 9. And we are allowed to place basically we are allowed to place cows in the same tower as long as no two like cows differ by no two cows differ by less than k. So an example is, let's say I have a tower of, so I can build towers like this. I can have a tower of cows. Suppose k is equal to 1, then I can build a tower with weights 3, 4, and 5. So this would be valid because any two cows differ by at least 1. I could build something that's like 2, 4, 6, 7, 9. This would also be a valid tower. But now let me give an example where, say, k is equal to 3. Then a valid tower will be 3, 6, 9, 12. This will be a valid tower. But an invalid tower would be 3, 6, 8, and 12, because 6 and 8 only differ by 2. So this will be an invalid tower. And then, of course, I can't have like two equal weights. Like something like 3 and 3 is blatantly not allowed, since that would be difference of 0. Okay, so we got the definition of towers out of the way. So now what we want to do is, using the fact that we have at most m towers, we want to try to place as many cows into towers as possible. So we want to maximize the number of cows used in towers. We don't need to maximize the number of towers we use or anything like that, or total weight or anything like that. We just need to maximize the number of cows that are used in towers. So how can we approach this problem? Well, there's a lot of parameters kind of flying around, and it might be a little daunting at first to just like try to attack this problem head on. So we can try to reason about this in some sort of, let's say, a greedy sense, because when constraints are large, typically a greedy solution is like one of the only is something the only type of solution that is feasible. So let's say we consider building some towers. Let's consider the first the minimum weight cow. So consider the minimum weight. Well, then, from a greedy perspective, it would make sense to try to use as many of these minimum weight cows in towers as possible, right? Let's say I want to place them as like a bunch of, suppose the minimum weight is 2, then maybe I want to start by creating a bunch of towers, that all have 2. Um, and it would make sense for me to put these cows in towers with weight 2, because suppose I don't use one of these cows and I instead like save it for a cow that's going to have weight 3. then that's only going to decrease my number of options in the future, right? Because a tower that has 2 on top versus a tower that has 3 on top, the tower with 2 on top has more options. If k was, because for 2, I can put anything starting from 2 plus k, 3 plus k, 4 plus k, so on and so forth. But for 3, I can only start placing from 3 plus k, 4 plus k, and so on. And so from a greedy perspective, I want to minimize the tops of these towers, right? So that's the first bit of greedy intuition we might have. And so this kind of motivates us to maybe start looking at this from maybe sort the cows and consider them from smallest weight to largest weight. So let's try doing something like that. Let's try sorting by weight. So we're going to sort by weight. We're going to have a bunch of towers. Initially, let's say we have a bunch of towers. Let's say they initially all have negative infinity at the top. So the idea is that these towers are going to be built from I guess bottom to top, and the weights are going to keep getting larger. Initially they all have negative infinity because you can place anything on top of them. There is no restriction. And now let's say we have let's say our total list is we have 2 cows of weight 2, 3 cows of weight 3, 1 cow of weight 5, 1 cow of weight 8, 1 cow of weight 9, 1 cow of weight 11, something like this, right? So we have a bunch of different weights. And let's say k was equal to, let's say k is equal to 2 in this problem. So if I'm processing all of my weight, first I consider the cows of weight 2, right? I consider these 2s. And I can choose to put the 2 on top of some towers. So maybe I put them on top of here. So now these towers have cows of weight 2 on top of them. So this would already increase my answer by 2 plus 2 because I used 2 cows. Now, something that might come to mind is if we want to use all these cows. Maybe we choose not to use one of these cows. We choose to not use it. But if you think about it for a bit, it doesn't make sense to not use a cow because whether you choose to put like this cow with weight 2 or put some other cow with weight 3 later on, both of these contribute just plus 1 to the answer. So it's like if you choose to give up this cow spot to get a cow later, that's plus 1 either way to the answer. And if we're going to take like a cow no matter what, we want to take the cow as the smallest because that creates the most number of options in the future, right? Like having a 2 on top, it gives more options than having a 3 on top. And so from a greedy perspective, we always want to use the 2s. We always want to use a cow whenever we can. So let's go ahead and use both these cows. Both of these have 2. Now we have move on to weight 3. 3 is going to have not enough. Actually, for the sake of example, I'm going to add one more cow of weight 3 just to showcase this. So for 3, I want to place all these cows if I can, but I only have 5 towers. I can't place them on top of here, but I'll place them on top of here. And now you can see I've used 3 cows. I've contributed plus 3 to my answer. Unfortunately, I have nowhere I can place this 4th cow, so we're just going to skip over it. Now let's move to 5. So for 5, we can choose to place we can place the 5. We can place it here, or we can place it here. And I guess if you look at this, from a greedy perspective, it makes more sense to place it on here because this minimizes the overall set of cows that we have, right? This makes it a 2, 2, 3, 3, 5, whereas this one makes it like 2, 3, 3, 3, 5. So instead of a 2, we have a 3. Now, so therefore, you could say that it is greedily optimal to place it on top of 5. But interestingly enough, for this problem, it actually does not matter which one we place it on. We can actually place it on the 2. And the way you can prove this is suppose that you're placing it on the 3 because you want to save the 2 for something else. Well, then that something else can also be placed on top of the 3 because that something else is going to be greater than 5. So it's also going to have distance at least plus 2 from 3. So actually here it is okay for us to put the 5 on top of the 2 or on top of the 3. Let's just place it on top of the 2 for now. And I make this distinction because it's going to make the implementation of the algorithm much easier later. So let's say I place the 5 here. So I place the 5 here. Now the 5 is done. Now I'll move on to 8. I'm gonna place it. Let's say I place the 8 here. Also move on. The 9, I place it here. Move on. 11, I'm gonna place him here. Move on. And then 12, finally, I place it here, move on. So here I have placed all but one cow, which is a pretty optimal answer. It's the best we can possibly do for this test case. So what exactly have I described here? Let's actually outline a concrete algorithm now. So here's the idea. I'm going to have a minimum priority queue. So a priority queue that brings the minimum to the top. And I don't want to have like 10 to the 9 different towers inside a priority queue. That's too much memory. I want to compress it. I'm going to store pairs. And I'm going to store pairs of representing the tower. It's going to be the weight on top of the tower and the number of towers I have of this with this weight. So it's compressed form, basically. I'm going to store this priority queue. Initially, it's just going to have one pair of negative infinity with m of these. And then what I'm going to do is I'm going to go through each of the distinct weights one by one. And what I'm going to do is keep hopping from this priority queue and add cows until like two things happen. Either one, the PQ is empty, or two, the top of the PQs, the minimum weight, top of PQ plus K is now greater than the current weight we're trying to place. So we can no longer place this weight cow anymore. I already see there's maybe a few questions. I'll get to that in a second. Yeah, but let me finish the explanation first. So yeah, basically I want to keep adding cows. I'm basically just going to greedily add cows by popping out the priority queue and adding it to the topmost. Yeah, adding it to the smallest weight each time. And then at the end, I just need to add. At the end, I can just add like one like weight. Let's say weight WI with the new count. And so what is the complexity of this? Well, the complexity of this is that each time there are kind of like two cases. Um, each time we process for priority queue, either it's removed forever, or or we ran out of the cow, which can only happen at most once. So the total amount of work we do is bounded by, we'll say, order n log n. Because each pair is added, there are only at most O of n pairs that can be generated, and each pair is added at most once and removed at most once from this priority queue. And the proof of correctness of this algorithm is what I described above. So you always want to use a cow whenever you can. And yeah, you always want to use a cow whenever you can. And there is no reason to, like, you always want to keep it as minimal as possible. And then finally, basically it doesn't, when you have like a tie between different towers and you add it to, it actually does not matter. So in our algorithm with the priority queue, we're always going to be adding it to the smallest weight tower, or that's the weight tower with the smallest weight on top. All right, so that summarizes this problem. I'm gonna go ahead and take a look at the chat now, see if I'm gonna take a look at the chat now. All right, starting with the first one. Should two pointers also work? Um, Actually, yeah, now that I look at it, for this part, you don't actually need a priority queue because the priority queue is always going to be like, you're always going to be adding something with the largest weight to the priority queue, like larger than anything else so far, and you'd always be removing the smallest one. So actually, you are correct that we could substitute this priority queue for some sort of two pointers instead, where basically you have like one pointer for where you start for the next tower to add to, next tower to add. And then you have one pointer here, and then you have one pointer for like the current weight. And then both of these will always move forward. And so that would actually reduce this part of the algorithm down to O of n. Although the overall algorithm is still n log n because you still have to sort. So the sort still makes it n log n. But it is true that we could use a two pointers for the second part and save it and like make that part like slightly more efficient. Yeah. Let me see if there are any other algorithms. Or sorry, let me see if there are any other questions. Yeah, was time complexity, so that'll be yeah, as I stated. And log n. Because I think you have to do a sort regardless. Yeah. And someone's asking about problem 3 now, so we will cover that. We will cover that soon. All right. Any other questions on problem 1? Oh, cool. So actually, a quick question. Yeah, one more question that someone sent me. So how do I add as well as pop in the priority queue? So the idea is that I guess this is kind of a two-step procedure. The first is that when I'm processing a wait, I'm going to continually pop from the priority queue, and until I get pop from the priority queue and increment the number of towers that are going to have WI at the top. And then at the end, I'm going to push one like extra pair of WI number of towers I have into the priority queue. And I think you might also need to do one more push because you might use up like one pair partially. So it might be that there was some entry that we popped in the priority queue. We used some of the towers, but not all of them because we ran out of cows of WI. So we need to put that pair back into the priority queue. So actually, yeah, we have to do at most per two pushes per I, which is still O of n pairs in total. So it's still n log n. But yeah, that's a good distinction. All right. So the second problem, let's move to the second problem now. So the second problem was one about labeling barns. So we have a bunch of barns. We have n less than equal to 5 times 10 to the 5 barns. And they form some sort of like connected network, basically just a graph. They're just a graph. And actually, basically, we specifically so there's a cycle. So there's a cycle of length k. K is just less than equal to n. And there are two different labelings from Annabelle and Bessie. So A and B. So basically, each person is going to look at this graph and give each like vertex some label from 1 through n, and it's a permutation of 1 through n. So maybe person A labels it like 1, 2, 4, 5, 6, and 8, and person 2 label it, and then they label like there are also some isolated vertices. So they label these ones like 3 and 7. And then the other person or the other cow label it, let's say they label it like 1, 2, 5, 6, 3, 8, and these ones they labeled 4 and 7. Right. So basically, there are different labelings, or basically there are two different labelings on this graph. Now you don't actually know the exact labeling. All you know is that one person or one cow labeled it like a certain order around the cycle, and the other cow ordered a different some ordering around the cycle. So all you know is like what order the labels appear in the cycle, but you don't actually know where the starting point is or which direction the cycle you went in. And now you want to know, basically, what is the maximum possible labels that could coincide between the two cows? So, to give another example, let's say that one of the arrays was 1, 2, 3, and the other one was 2, 3, 1. This is just the order of around the cycle. You don't actually know what the label is, but the labeling for this one could have been that this was labeled 1, 2, 3, and this was labeled also 1, 2, 3, and they just started reading it from here instead of from here. And in this case, this will be 3 labels that coincide, which is the maximum possible for this test case. So yeah, so how can we approach this problem? Well, First things first, before anything else, we can observe that any label not in the A or B, that's just an instantly +1. So if there's a label that does not appear in either A or B, so a label that does not appear inside the cycle in both graphs, in both labelings, then we can just have them both assign that label to the same vertex. And then that's just instantly like +1 to the answer. Now we need to worry about the cycle. So basically, what this is really asking is that like we have two different labelings, and we just need to find a cyclic shift of one of the labelings, possibly with reversing, to make it have the most number of matches with the other labeling. So we just want a cyclic shift possibly with reverse, so that the maximum number of matches. So of course, since n is large, we can't manually try every single shift, but we can observe that in this particular problem, the labels are distinct 1 through n, right? It's a permutation overall. And so that's a pretty big deal because that means that we have like one label, like 1, 2, 5, 3, 4, and the other one was 2, 3, let's say 6, 1, and 5. Then for each one, there will exist a unique position in the other array. And each label inside one of the arrays, there's going to be a unique position that appears in the other array or does not appear at all. If it does not appear at all, then there's no chance of getting that to align, so we don't even worry about it. But if it does appear, say it's 2, then we know that if we shift it by 1, if the shift is equal to 1, then we will get +1 to the answer. So here, if we shift it by 2, we get +1 to the answer. Here, if we shift this one, if we shift it by, let's see, if we shift it by 1, 2, 3, that's also +1. And this one, we need to shift by 1, 2, right? And so what we get here in this situation is that if we shift it by 1, we get 1 alignment. If we shift it by 2, we get 2 alignments, both the 1 and the 5 line up. And if we shift it by 3, we get 1 alignment. So here 2 is the maximum, so that's the answer we take. Right, so what we can do is we can just go through, instead of trying every single cyclic shift, we just go through each array or each element of the array, check where it exists inside the other array, and calculate just like how much we get shifted by, such the difference between them, mod k, and then put that like +1 to like that shift amount inside like some table. And then at the end, just take the table entry with the maximum value. And then, of course, it is also possible that one of them was red going this way, and the other one could have been going like the other way. So you also need to try like reversing this array and then rerunning the algorithm again. So you can just like run the algorithm twice and reverse the array in between the iterations. And so this will work in O of n time overall because at the beginning, like checking the ones that don't appear as O of n, doing the cyclic shift, or like calculating for each array, for each element where it exists in the other array, that's also O of n. If you just pre-compute that information, everything can be done in O of n. All right, so any questions on the second problem? Let me see if there are any questions in the chat. It looks like people are also discussing the second problem as well. So yeah. Okay, then we have one more problem to cover. So let's go ahead and cover that real quick. The third problem was about target practice. So in this problem, we have less than equal to 10 to the 5 targets and C less than equal to 10 to the 5 commands. So we have a number line. There is a number line. There is a number line. You initially start at position 0, and then you basically go through all the commands one by one. Each one, you have a string of commands to go through. Each one can be one of three options, F, L, or R. L and R just means that you move one to the left or one to the right. And then F means that you fire, like you fire at the current position. And if it hits a target, then you get like, if it hits a target, then yeah, you hit a target. Yeah. And so now, basically what you want to do is you want to calculate the number of distinct. So you only count if you fire the target multiple times, you only count it once. So you want the number of distinct targets that you hit. And also, you don't just want to calculate this. You are allowed to, you want to maximize the number of distinct targets you hit if you are allowed, if you can change at most one command in the sequence. So at most once, you are allowed to go into the sequence and you can change like an L to an R or change an L to an F or make some sort of change to try to maximize the number of distinct targets that you hit. Okay, so that's the problem. Let's talk about how to solve it now. So I'm going to say right now that there are many different solutions to this problem, many different solutions that I know of, and they are of varying levels of implementation difficulty. So I'll present a solution that I think is relatively clean and short to implement. It's like probably less than 100 lines, which is considered short for this problem. So let's do this. Um, So first thing we can observe is that so the first observation we can make is that the ending coordinate can shift by at most plus or minus 2. You can't shift more than that. The way you can shift 2 is if you change an L to an R. If you change an L to an R, then instead of moving to the left by once, instead of moving left once, you'll move to the right an extra time. And so your overall like ending coordinate will be a +2. If you move from a right to change to L to R to L, that's a -2. And then everything in between can be done with some sort of other change. So the point is that either ending coordinates can shift by at most plus or minus 2. And so what we can do is let's just fix what the ending coordinate is. There are most 5 options. We'll just run the same algorithm 5 times. So what we'll do is we'll fix the ending coordinate. And now the second thing is there's this tricky thing about distinct targets, right? We have a distinct we only want to count each target at most once. That's kind of finicky. So as an aside, let's prepare a subproblem. If I have this black box data structure, what I can do is I can add some x, I can remove one occurrence of x, and I can count the number of x with at least one occurrence inside the data structure, right? This is just a subproblem. And this subproblem can be supported in O of 1 for every operation. Because what you do is you simply have a frequency table. You have a frequency table. And then when you have an x, you just like plus like frequency of x or like minus frequency of x if you add or remove an element. And then when it drops to 0 or when it goes to 1, you +1 or -1 from your count. So you also keep track of the count. Like plus the count. So that's our subproblem here. We have this data structure that's able to just kind of black box, like add elements, remove elements, and count the number of occurrences, count the number of X with at least one occurrence. Okay, so why do we care about this? Now let's actually talk about the algorithm itself. So we fix the ending coordinate, right? We fix the ending coordinate. So what we'll do is we'll first walk from the ending coordinate backwards. So we'll first simulate backwards. From the ending coordinates that we fixed. And we'll just add all the targets that we hit. We add all the targets that we hit into our data structure. And we don't have to worry about like making sure we only add a target at least we don't have to worry about adding a target like at most once because our data structure, this black box, already takes care of that counting for us. It already takes care of the annoying part of like making sure that we only count a target once if it's hit multiple times. So we actually just add it every single time and let the data structure do its work, right? So we add all the targets to our data structure. And now what we'll do is we're going to sweep from the front. We're going to sweep from the front for where we change. So we have the sweep line here. It's moving to the right. And as we move to the right, we are going to, as we move to the right, we're going to remove the targets that we hit from the back, like based on the ending coordinate simulation, and we're going to add the ones that we hit from the front. And then at each coordinates, we just manually like try, like we brute force iterate over every single possible change, and we allow the change as long as it would cause the alignment to be correct, as long as it would result in the ending coordinate we fixed at the very beginning. So we just sweep from left to right. We as we sweep, we add the coordinates based on the start, and we remove the coordinate based on the end. And then we just try at each position all the changes. When we sweep to the points, we also try all the changes. So we try like changing like say we change an L to an F, then what we can do is we can just add this coordinates to the black box, data structure, query the data structure for the answer, and then roll it back. So just remove it from the data structure, and then keep going. And then similarly, if we change like L to R, in this case, there's no adding to the data structure. But the point is that like if you do like an F, if we change like say an L to an F, we can just add our current coordinate to the data structure, check the answers, take the maximum of the best, take the maximum with the current answer so far, and then roll it back and then keep sweeping. And so with this solution, this would work in O of n time. So there's a constant amount of work where we have like a constant factor of 5 for each ending coordinate. We have a constant factor of 3 for everything we change into. But other than that, it's all O of n. And yeah, the reason I present this solution is because I think the trickiest part of this problem was trying to get the distinct coordinate stuff correct. And you might have had issues where like if you pre-compute from a prefix or suffix and then you change something in the middle has to be like treated differently than like the beginning or the end. So this data structure kind of like gets rid of or does all that work automatically for us. So we don't have to like worry about the details of what happens with that. And this works in O of n. Yeah. So any questions?
There's some discussions on the chat.
Yeah, I'm reading the chat now. Yeah. I'll scroll to the top. There's a lot to read.
Take your time.
Yeah, so what black box being used? Yeah, so you can use a map, that's fine. Or you can just use like a giant array. The frequency table can just be a giant array of like size like 2 times of size 2 times c plus 1 because you can go to at most negative c or positive c. So it can just be a giant like array. Yeah. How do we check the duplicates in O of n? So that's what the data structure is. So the idea is that I can add something multiple times, but maintain this counter that only counts it once. So the idea is that when I do like plus the frequency of some element, if it hits 1 for the first time, then I do like count plus plus. Right. And similarly, if I do minus minus the frequency, if I reduce the frequency of some element, then it hits 0, then I decrement the count by 1. So that's how the data structure maintains the count of duplicates. Yeah, someone said this is their solution, but it's just a bug somewhere. Yeah, definitely the tricky part of this problem was definitely uh trying to implement this correctly with no bugs. And they're actually like this is I mean, and then that also depends on what algorithm you choose as well. Some algorithms can get a little bit, some like other solutions can get messier. Yeah, what alternative solutions are there? Um, yeah, so like one other solution I had in mind is like to do some sort of like calculate a prefix and suffix and then like use some sort of use some sort of like table to check like only count it like +1 if it's the first occurrence or from the front or the last occurrence from the back. And they do some casework on what happens if we change. But that gets messy fast. That there are probably also other ways you can like deal with this condition or try to count this. Yeah. Yeah, so that's why I like this approach because it kind of relegates the work of dealing with duplicates to the black box data structure, and then we just sweep and try. We just sweep and try every point. All right. Any questions on this problem or any of the problems that we covered? Yeah, still kind of confused while we roll back. Yeah. Um, I guess I can give a little more concrete example. So the idea is that if let's say you sweep from the back and the coordinates are like let's say the coordinates are like let's say from the front the coordinates are 0, 1, 2, 1, 0, -1, -1, 0, 0, and 1. But now we sweep from the back, we shifted by 2, so it's gonna be like 3, 2, 2, 1, 1, 2, 3, 4, 3, and 2. And what happens is initially we sweep from we go from the back and we add everything to our data structure based on these coordinates. And then when we sweep from the front, we add these coordinates and we remove these coordinates. And then we just need to make sure that whenever we make a change, the change needs to be such that it like lines up. So we're trying each position and making a change. Yeah, so that's the interesting thing. Is our data structure is already, so at any point, our data structure will already have the entire suffix and this prefix so far inserted, and it will have automatically computed like the number of duplicates. What do I mean by line up? So yeah, as an example, here we have fixed the ending coordinates to shift by 2. So it needs to be changed. So it needs to be that we change like, we need to change like an L to an R. That's the only way we can get a shift by 2. And so at any point, we only allow changing, like say an L to an R. That's the only valid change. So we don't like allow like if we for example change like an F to an R, that doesn't create the right ending coordinate. So we can't count that as like we can't count that as a possibility. So that's what I mean by line up is that like when we consider a sweeping, we only consider changes that cause like the correct ending coordinate. Yes, we can just loop through the possible changes. There are only at most 3 for every coordinate. Yeah, and then there are adding positions where we can change it. Yeah, and we already fixed the ending coordinate out in the outer loop. Like there's an outer this entire algorithm is being run 5 times, once for each outer once this entire algorithm is being run 5 times, once for each ending coordinate. Yeah, how do you add all the positions at once? Yeah, so the idea so it's like we add all of these coordinates first, and then when we sweep from the left, yeah, we sweep and then when we sweep from the left, we start adding these coordinates and start removing these coordinates. And what I was talking about with the rollback was that let's say we change an L to an F, then this is like an extra fire that's not accounted for. So when we change the L to an F, we first add the F, we add the current coordinate based on the F, we check our answer, and then we remove the F. So we change it back to an L, and then we keep going to the next position. So that's what I was talking about with the rollback. Is like sometimes if you consider changing to an F, you may have to temporarily add like a new coordinate and then remove new coordinate for this particular case, and then consider the answer, and then take it out and keep going. Am I sweeping on -2, 2, 1, -1? Where did those numbers come from? Or oh, so that's actually that's if that's the offset. We fixed the offset on the outside. So we run this algorithm like 5 times in total, like once for each possible like amount of offset, like 0, 0, 1, -1, 2, and -2. Yeah. So maybe I could write some quick pseudocode to show how this works overall. So basically, do like a for loop for each ending coordinate. Yeah, for each ending coordinate, 5. Uh, we first uh we first go backwards and add all to our data structure, and now go forwards. So like I say, I from 1 to n, and for each one, we iterate for each of you can actually do this a little more efficiently, but it doesn't really matter. The way I did it was I just iterate over for each f, l, and r. Try the change. If the offset is correct, if the offset is correct, then the answer is going to be the maximum of the answer. We update our answer with the current like data structure like value. DS count. So this is at most 3. This part's at most 5. This part's like n. So this is O of n. Yeah. Yeah, and the 3 per string is just like I'm trying like for each position. Actually, I guess you don't have to try all the possible characters because only some of them are going to be like valid. But I mean, I was just being a little like simplistic with the explain with demonstrating this since it's all like O of n anyway, so it doesn't really matter if you do an extra factor of 3 or whatever. No, we only make at most one change, right? So there are n places we can possibly change, and each one can change to 3 options. That's 3n. So that's fine. Yeah, so there are at most n possible locations. Yeah. So n possible locations for a change and 3 for each. Yeah, so it's 3n, which is still O of n. Mm. How does reverse sweep accurately account for move to right for all other commands? Um, so I guess going back to this diagram here, the reverse sweep is the first like put all of the reverse sweep is the first put all of the coordinates based on the ending coordinate, all the coordinates into the data structure, where these coordinates are based on the ending coordinate. And then these ones are based on the starting coordinate. And so when you like start sweeping from the left, when you start sweeping from the left, you're adding these elements and you're removing these elements. And you just need to make sure that change is such that like you need to make a change. Like here, at some point you need to go from like the 2 bridge over to this 3, right? So you just need to make sure that like the change you make like is appropriate, like it gets you to the correct offset. So that's the part. So that's how you're like linking these two sequences up basically. It's like you're changing like say this is an L and you change to an R, that's valid. So that will get you to this. If you replace this from an L to an R, so that's like the middle part here, then this part is now bridged with this part. There are multiple targets, how they switch to work. Oh, you don't do this once for each target. It's like your target is just like the target is just like when you add it. When you add it, I guess you also have to check like is this coordinate like a target? Yeah, that's just like a quick if check. So at the very beginning, you just like have like a Boolean array of like target of X is true if there's a target at coordinate X and false otherwise. And then you just like when you add it, you just need to make sure you only like count it if it's actually a target there in the first place. Otherwise, you can just ignore it altogether. Yeah. Any other questions? Yeah. I think this one was undoubtedly the hardest of the three. Just because like even if you get the right idea, you still might have like not be able to like fully implement it. Mm. Okay. Then I think let's go. I'll stop screen, share my screen, then we can go back to the slides. Yeah.
Yeah, thank you, Max. We have two more slides to share here. Here is the summary page. How the Max just give us a quick summary of these three problems and the corresponding XCamp courses.
Yeah, so I put some, I guess you can say tags here for what topics you might need to be able to solve these problems. And then there's some classes here that go with it, or there's some courses here on the right that go with it as well. Yeah, and we have a Discord that you can join for more live solution discussion if you want to keep discussing these problems. Yeah.
Yeah, thank you, Max. Let me copy this to the chat. Please join our Discord channel. So we will post even the future events, future activities here. Also, please, fill in a form about your scores so we can give you, here, I think here's in the next slides, we can give you a detailed report card. So here's the link. You can see it's in the chat too. So after this contest, I think all of you kind of eager to know kind of some analysis on the result. Please share with you your score for each problem, so we can give you a pretty detailed report like here. In addition, at XCamp, we provide a series of classes. First is on-site camp is coming. It's from 26th to the 30th in San Jose. It's 1 week from 9 to 5. If you want to improve your coding, especially the competitive coding, the USACO results in the coming sessions, please join our on-site camp. It's very effective. It can be improved. Also, we have a year-round weekend class, especially we have grandmaster classes for USACO Gold, Platinum, and US Camp, also even at the ROI level. APCS is another one if you need any help on that. Okay, great. Thanks again. Thank you, Max, for the solution session. Maybe last call. Any other questions? No? Okay. Thank you all. Wish you a great holidays. Okay. Thank you, Max.